Hey guys, my name is Jani and this is Optofidelity Test Corner. This is the second episode of a series of episodes where we talk about waveguides. And in the previous episodes we talked about what are the waveguides, and then in this episode we talk about the design, some problems that might happen during the design, and also the manufacturing of waveguides. I have here Product Manager Joonas Pylväinen from our Finland office. Joonas, welcome to the show.
Thank you very much. Thanks for having me for the second episode as well.
Good to have you here. So Joonas has been working in his previous life in Microsoft and has been working with the HoloLens project there. So he has a lot of understanding on how these waveguides are made. So Joonas, let's start talking about the design process of the waveguides.
So the design process of the waveguides, that is a very complex topic, and I would say at the moment there are quite many different processes that you can make there, and most of the manufacturers, I would believe, they have their own software or their own custom simulations that how they are running the design process or design iterations for the waveguides. There is also commercial software available, these classical optic software that are quite common, that can also simulate the waveguides, but on that level you need to be very deeply into the design parameters and the science behind the waveguides, that how are they actually function, that what are you doing with the elements or the optical elements, and how you are kind of optimizing them. So it's kind of a very complex topic.
So it sounds like you need to be optical designer in order to do something like this.
Indeed, and besides being optical designer, probably be very well versed in the field of nanophotonics as well.
So when you are doing design, there's always trade-offs. Like you choose to have some feature that is really good, but then you end up having another feature to be bad. So how about in the waveguide design? Do we have the similar trade-offs?
Of course, like in most cases in real life, there are trade-offs. So the perfect waveguide can of course be designed, but unfortunately it cannot be manufactured, at least with the current technologies, and probably not in the near future anyway. So when doing the kind of a trade-offs, usually you are trying to achieve something like a large field of view, or have all colors RGB in a single waveguide instead of having 3 separate waveguides. And now when you are kind of for example increasing the field of view, you might be lowering the efficiency over the field of view or over the eye box, for example, or kind of disrupting the color uniformity of the image at the same time. And now again, if you want to improve this, it might be that you need more plates or more waveguides stacked together, for example the separate RGBs, but then the trade-off is of course in the size and the weight of the display, or the final display of course.
So sounds like that is a quite challenging optimization problem.
Indeed, it's very challenging, and of course you need to take into account that what materials, for example, are available, what is the refractive index of the material you are going to be using, and then also the manufacturability, that how your design is transferring to the actual product, because it's not one-to-one.
Well, good that you brought up the manufacturability. How does the manufacturing process go for the different waveguides?
So for the holographic waveguides, if we start from their example, basically the pattern or the hologram is exposed on the material on top of the glass. So the material is usually some type of resin or resist. Then with the diffractive waveguides, one of the popular technologies there is nano imprint lithography, where you are stamping the pattern onto the waveguide. And then on the reflective waveguides, you are basically stacking these partly reflective mirrors on top of each other. So very much different from the two previous ones. So it's more of a manual assembly, or let's say a straightforward assembly, at least on paper.
Okay, so if we look a little bit deeper, for example, this stamping method, I believe that we have a graphics for this, so how would that go? What are the steps there?
So for the diffractive waveguides, so this stamping method, basically you first have your hard master, which is the kind of hard copy of the pattern you are intending to use. It has the gratings on it, and basically with that you stamp this kind of intermediate soft stamp first, which will have the opposite pattern, of course, because you are stamping it. And then you are using this softer stamp then to kind of transfer or stamp the pattern onto the final wafer.
So why do we have this soft stamp? What is the point of doing like intermediate stamp?
Well, the hard master, of course, you could stamp with it as well, but they are very expensive and difficult and slow to make and require great accuracy to make. So anyway, you can kind of save it from being deteriorating is good. So that's why when you use kind of an intermediate stamp, you are basically using that intermediate stamp to save the hard master. For example, with one stamping of the hard master into the soft stamps, the soft stamp can be used tens of times, and it saves tens of times from the hard master from being used.
Okay, well that makes sense. Then I can see that in our graphics we have this word nil. What does that stand for?
Yes, I actually mentioned it already before. So it's coming from nano imprint lithography. So basically, nano-sized structures are imprinted or stamped on the wafer. So that's where it's coming from.
Okay, good. And then when we go forward, what happens next?
So after the stamping process, you have your wafer with the pattern, the final wafer. It could go to some sort of coating, for example, depending on how the process is designed. But most likely, you are ending up with a wafer which has, let's say, 4 or 6 different DUTs or even more DUTs, so devices or basically the waveguides on the wafer. So you need to separate them from each other. And that step is called dicing. So you are using a laser dicing machine or something similar to cut out the waveguides into individual waveguide displays.
Okay, so after that then you have those individual waveguides which most likely looks a little bit like, for example, sunglass lens or something like that.
Exactly, yes.
So then I can see that we have this stacking process here. What does that mean?
Well, actually, before we can go to the stacking, now that we have done the dicing, the plates are probably, or the waveguides are probably pretty dirty. So it might be that you need to clean them out with air or something to get the kind of particles out of them. And now the stacking process then, depending if you need the stacking process, you might not need it at all if you have a single waveguide design on hand. But if you are using the multiple waveguides like RGB separately, then you would have these as basically in a separate material stocks, and you would start gluing them together. And after that process, you would then have a stack of 2 or 3 or more waveguides glued together. So that would be the kind of a final step of the waveguide itself.
Okay, and after that, when you have basically that stack ready, then you could then basically make a module out of it, which would have, I guess, the projector connected to it.
Indeed. Now again, depending on how it has been designed, but after that you could glue the projector onto the waveguide, or have some kind of an assembly or a holder where you can put the projector onto the waveguide. And then after you have done that, you might have the display already ready, or you might have to do it for the left and right eye separately as well.
Okay, and then you basically have like waveguide display on your hand, which you can then put into the final device.
Exactly. Then it's just about the mechanical assembly of getting it into the AR glasses.
Okay, so of course many things can go wrong. So should we now talk about what can go wrong in different steps?
Yeah, that sounds like a good course of action.
Yeah, so if we start from the beginning, there's the master. So what can go wrong there?
Well, of course, with the master, you are affecting everything that happens downstream. So all the defects there, they are propagating to the fully assembled unit as well. So even the mastering process itself, you are somehow exposing the pattern onto the glass there. So, and also doing some development, etching maybe. And if the gratings are not there as per design, then everything of course will be affected downstreams there. So there are multiple steps involved that involve exposing, etching, or some kind of a development there in between. And for sure, when doing all these processes, the kind of cosmetic quality is at risk for the master itself as well. So if you get a scratch there, that scratch will be in every display you are making after that.
And then that would of course affect the image, the perceived image quality in the final product.
Indeed.
And then how about the soft stamp and then the nil? I guess those are pretty much kind of similar situation there.
They are similar as well. The key here, of course, is the replicating the grating design perfectly, or as perfectly as possible. So in every step you are stamping the pattern. You are kind of degrading it, because it's a physical process. So the gratings can physically break or bend or kind of disform in other ways as well. So that's the main thing there. And in every step you have your own chemicals and your own materials that you need to use, and they might be very, very sensitive to the process window, so the kind of process parameters you are using. So everything is very sensitive there.
And since we are talking about structures that are a size of a wavelength, not much need to go wrong when the image quality will be affected. Even like temperature changes might cause problems.
Exactly. Temperature changes could be some mechanical fault in the tools even, or something that is not related directly to the design or the hard master as well. Could be also even the ambient temperature, not necessarily the process temperature.
Yeah. And then when we go to the dicing, how about there?
Well, in the dicing, we're always working with glass and substrates. It's a risk that you kind of chip the edges when you are dicing them. Usually some sort of a laser is used, so manually dicing with the knife, for example, that's not an option in manufacturing. So you need to use kind of highly capable kind of a laser dicing machines there. But every time you are kind of cutting out a piece of a waveguide, there's a risk that the edge might chip or crack, for example.
Mm-hmm. Got it, yeah. And then how about when we go to the stacking?
Well, in the stacking, many things can happen. For example, one of the key things for especially with the reflection mode waveguides or the mirror mode waveguides is that the stacking alignment between the plates is accurate, so they are not kind of mismatched. And also could be that when you are putting them or making the sandwich out of them, that the relative gap between them stays as per specification. And of course, if you are doing the stacking, you somehow attach them to each other as well. So you are most likely using some sort of a glue there. So the glue can also cause kind of, if not changing the physical distances between the waveguides, it can look bad if it's spreading around, for example. So the cosmetic quality again.
Mm. And then you said that when we have, for example, diffractive waveguides, we might have actually, like, for example, one waveguide for each color. And then when you stack those on top of each other, if they're not perfectly aligned, or they are, for example, at different angles, that means that then the perceived image quality, the person would actually see the colors separating from each other.
Exactly. If you have this RGB stack and you have all the plates bending and in different angles, it will cause that in the end result you have all the colors coming out in different angles. And in the worst case, your image might be that your parts are moving away quite a bit. But then on a smaller scale, it would mean that perhaps some edge of an image or edge of an object has some discoloration or kind of a bit rainbowish kind of edge visible.
Mm. So basically the colors, the primary colors kind of separate from each other.
Exactly.
Mm. Okay. And then when we go to module assembly and we are basically then attaching the projector to the waveguide, what is most important there?
Well, of course, alignment of the projector, that you are in coupling the light into the correct place in the optical element. So if you are off by a lot, you might have well, in the minor case you have poor efficiency because not all light is coupled in. But if you are going far enough from the kind of a specification, it might be that the image itself is not looking what it is supposed to be. So that is also in the plane, but the angle also can affect there. So the angle of the projector, how it's being attached. Mm.
So yeah, so basically then if the angle is also wrong, then the efficiency might go down, but also the image that comes out from the waveguide might come in a wrong angle, and then it wouldn't basically couple with your eye perfectly.
Exactly. So you are also, in the worst case, you might be cutting out the field of view. So instead of seeing it all, you might be seeing a smaller part of it or cutting it out from the edge from some direction.
Yeah, and then the user wouldn't, for example, see the full user interface that is shown on the device.
Exactly. The small start menu on the corner,
yeah,
might be cut off as well.
True. Okay, hey, good. Thank you, Joonas. This was really enlightening, and then now we understand what could go wrong in the design and the manufacturing. So in the next episode, we will dive a little bit deeper on these different problems and how to root cause the problems in the manufacturing and design process. So yeah, thank you, Joonas, again for joining, and thank you guys for watching. We'll see you in the next episode.
Thank you for inviting me. See you next time.
See you. Bye.